So I was talking about the design analysis of a beam, and we have just looked at the determination of the effective span as as the first step that you need to do. And I have just said that the effective depth is the distance between the centers of the supports. If you have a simply supported beam, the distance between the two supports is the one that we call the effective length of that beam, and it is abbreviated by LE. Then we are supposed to size the beam, and I have just given this diagram, and I said that when you are sizing the beam, you need to determine the value of D, the value of H, the value of B, and the value of D. In this case, you can see that the D and HD are different in the sense that H is the overall length or the depth of that beam. D is the effective depth of the beam section, that is the distance from the center of the tension to the topmost part of that beam. Then you have B, the value of B. Then you have the value of D, D prime. We are going to see how you calculate each one of the case. So if I want to know the value of B, it is LE over 30, meaning that the LE, the effective length, the distance between the two supports, I divide by 30. Whatever I'm going to obtain is the value of B. Then the value of D is 2B. Is 2B. Then I have just said that B and H and D should be a multiple of 50 because they are the conventional values, and they will always start at 150, 200, 250, 300 like that, but 150 is the starting point. Then when you have D, you can be able to calculate the value of each. If you have the cover, then the bar you divide by 2, that is the reinforcement bar, you divide by 2. Then you add something that is called tolerance, which in most cases it is 2.5. Then from there you need to know how to compute the design loading. The design loading is the loading of the beam, that is the dead load and also the life load. The dead load is given GK, while life load is given QK. And we say that dead load is always the weight of, in this case, the weight of the beam that finishes the wall and the slab that is on top, while the life load is whatever is occupying, the weight of whatever is occupying that structure. Then, in this case, we shall be using 1.4 GK and 1.6 QK. That is 1.4 and 1.6 will be the safety factors of the factor of safety. And then we are going to multiply 1.4 with GK to get the design load of the dead load, and 1.6 times QK to get for the life load. Then from there, you go to step number 4, which involves you determine the design shear forces and the moments at any section. In this case, you must be able to calculate the maximum load. And if it's a simply supported beam, as you can see from here, it is the maximum moment is WL squared for 8 kilonewton per meter squared, while the shear force VA and VB is WL. You divide by 2. Then from there, I said that you need to come up with the shear force diagram and the bending moment diagram. And then you need to use the shear and the bending moment coefficient in order for you to determine the continuity of that beam. Then from there, we needed to design the reinforcement section. When you're determining the reinforcement section, or we are designing for the reinforcement section of the beam, you need to know that we are designing using BS 8110. And for that purpose, you need to have that table or those tables. And you need to understand each of the following parameters. That is, this is our rectangular beam that we are designing, the diagram that you can see there. The maximum depth is H, while the effective depth is D. And we have seen how you can be able to calculate each of the case. The same case applies to B. Then we need to know that AS is the tension reinforcement. That is, we always design the tension reinforcement at the bottom of that beam. Then at the top, we have AS prime, which is the compression reinforcement. You need to know how to determine the compression reinforcement. In this aspect, at this point of time, we need to know that you must always design for the tension reinforcement, but it's not a must that you determine the compression reinforcement, because concrete is very strong in tension, while it is also very weak in compression. Then you need to know that the D prime, the one that you can see from that diagram, it is bar divided by 2. That is the reinforcement, the diameter of the reinforcement bar. You divide by 2, you add to the concrete cover. You add to the concrete cover. Then from there, you need to know that the D, they are related in that formula. We also need to know about the following. That is, you have the cover at the bottom and at the top. They are covering the reinforcement bar. The bar divided by 2, as you can see, they are drawn either at the bottom or the top parts. Yeah, and you can see that the centroid of the bar, is given there. Then you need to calculate the MU, which is the ultimate moment of the concrete. And we are going to do it practically. You need to know that we have the neutral axis, NA. You have the distance X, which is from the center, the neutral axis, to the furthermost part of that structure. Then you need to know that we have the tensional zones and also the compressional zones. Then you need to know that that MU that we are calculating is always given by K prime FCU BD squared. K prime will always be 0.156, will always be 0.156. FCU is the maximum, that is the characteristic strength of concrete. We say that it is dependent on the strength of the concrete. Then we need to know BD squared. B is the value that we have calculated, the one we are assessing the beam, and D the same. So you need to square the D. And then you need to determine the step number B of the case. Step number B is whereby we need to determine if A maximum is greater than MU, so that you can be able to tell, that is, if the design moment, A maximum, which we have just said that it's WL squared of 8, is greater than MU, the one that we calculated using this formula. For A, the tension of the tension, if K, you also need to determine if K is, that is, K is equals to M maximum over FCU BD squared. You need to determine if K is less or greater than K prime, so that you can be able to determine you can be able to compare M maximum with MU. Then from there, we are going to be using this formula, that is A for the tension is given by M maximum over 0.8 FCU FYZ, where Z is the lever arm given by this equation that you can see here. And then from there, you need to use the table, as I'm going to show you. And AS provided is the one that is provided by the table. The area of the tension provided by the table should be greater than AS required, the one that you require, the one that you have computed. Then should always be greater than AS minimum, which is 0.13% of BH. Then from there, you need to go to step number C, whereby you are determining the maximum for A, B, and C. You determine if you require the compression part or not. If you require the compression, this is the formula. And then if that is a formula, then I will be able to do it later.